This conference will now be recorded.
Yeah, okay. Is my voice clear now?
Yeah, ma'am.
Okay. So, like, you're only going to attend the mock interview, or some others will also be joining?
No, ma'am. Only I, ma'am. Only me.
Okay. Okay. Okay, we can start with our mock interview.
Yeah,
You
okay,
can tell
ma'am.
me about yourself.
Yeah, ma'am. I am Rahul. I completed my graduation in Jain Institute of Technology, Davangere, with percentage of 70, and in the year 2022. And I pursued my training, DFT training in VLSI Guru Institute, with taking skills, some skills such as scan insertion, compression, ATPG, simulation, MBIST, boundary scan, etc.
Okay. Okay, we can start with our interview.
Yeah.
So the first question is, what is the difference between DFT engineer and functional verification engineer?
Yeah, ma'am. DFT engineer checks the verifies the design uh, without any requirement of programming or correctness of functionality. Not functionality. Uh, verification verifies the uh, it checks the correctness of functionality, where DFT checks the design, means hardware design.
Okay. Let me just share my screen.
Yeah.
Difference between DFT. You can mute yourself.
Yeah.
So difference between DFT. DFT with difference between DFT engineer and the functional verification engineer is so DFT engineer, what we do is we insert some logic, insert test structures, we insert test structures in the design to facilitate the detection of manufacturing defects in the chip. Facilitate the detection of manufacturing defects in the chip. So DFT engineers, what we do is we actually check the quality. We check the quality, whereas a functional verification engineer, they check they check the functionality. They check the functionality. So quality means whether our circuit is free of bugs or not. So that is what is quality. Functional verification means they check the functionality. And one more major difference is, say for example, if a particular circuit fails, if a chip fails, okay, if a chip fails after manufacturing, so functional verification engineer can only tell whether a chip is passed or failed. Tell whether a chip is passed or failed. So whereas DFT engineer, this is like functional verification engineer, they can tell only whether a chip is passed or failed. DFT engineer, we can give an additional information, that is we can also tell what manufacturing defect has caused the chip to fail. What manufacturing defect has caused the chip to fail. Okay, so say for example, if you consider one example, like consider one counter. You're having one counter. So this counter, just assume that it is failing. So that is, just assume that after 999, it again counts 999 instead of 1000. So functional verification engineer, they can only tell that the counter is failed. Functional verification can tell that the counter is failed. Whereas DFT engineer, they can tell what has caused the counter to fail. So we can tell what has caused the counter to fail. So counter can fail because of, like, say for example, MSB net, okay, is stuck at 0. That is why it is not changing to 1. Or MSB net is having slow to rise fault. Slow to rise. It has not risen within that time period. So we can tell, like, what has caused the counter to fail. We will be able to tell this additional information. Whereas functional verification team, they can just tell that the counter is failing because we are checking for the functionality. DFT engineers will be facilitating, we are inserting test structures in order to facilitate the detection of manufacturing defects in the chip. So we can additionally tell what manufacturing defect. So what manufacturing defect has caused the counter to fail. So that is like MSB bitnet is stuck at 0. That is why it is after 999, it is still counting 999 instead of 1000. Or MSB bitnet might be having like slow to rise fault. Within that time period, it has not risen to 1. So this additional information can be given by DFT engineer. And also, like, DFT engineers, they have various other advantages, like DFT engineers, they take less time to test a chip. DFT engineers, they take less time to test a chip. And also DFT engineers require less patterns, test patterns to test a chip. So these are other advantages of DFT engineers. So advantages of DFT engineers. So this is the major difference between DFT engineers and test engineers. So DFT engineers, test engineers, they will be checking the functionality, and if a particular chip fails, they can only tell whether a chip is passed or failed. Whereas DFT engineers, we are checking for the quality, that is, we are inserting test structures in the design to facilitate the detection of manufacturing defects in the chip. So if a particular chip fails, then we can also additionally tell what manufacturing defect has caused the chip to fail. So this is the difference between DFT engineer and functional verification engineer. You can explain like this with the help of an example.
Yeah, okay, ma'am.
Okay. So yeah, you can. Next question is, what is scan insertion?
Scan insertion is the process of converting non-scanned flops into scanned flops, and a register path is formed, which is known as scan chain path.
Yes, correct. So it is to convert all normal flops into scan flops and to stitch a scan chain. That is Q2SI path, the shift register path is formed. Yes, correct.
Okay.
And what is the need of scan insertion?
Ma'am, to gain controllability and observability in the every net of the flops or standard
Yes,
cells.
yes, correct. So can you explain like scan chain operation with the help of an example? You can draw it in either Paint or in your notebook. You can just draw it, and later you can share your screen and show. If you're drawing it in notebook, you can show it in camera.
Okay.
So scan chain operation with an example.
Urgent exam is complete.
Yeah. Ma'am, I draw it in notebook. Should I show through camera, ma'am?
Yes, you can show through camera. Mm. Yes, it is correct. So you can just try to explain it by taking like one small combo logic you can just take. You can take two patterns and you can just explain like what will happen during shift phase and what will happen during capture phase. Like say for example, you can take this example and you can just explain what will happen during shift phase and capture phase. Um, so this is scan chain operation. Scan chain operation example means you can tell like this. Operation example. So you can take a small circuit like this. This is SI. And then this is clock. This is flip-flop 1. And then this small combo logic only I've taken, just a NOT key.
Okay.
And then this is flip-flop 2. This flops Q, it is directly getting connected to the scan input. And this is the clock. And here, this is flip-flop 3. This is the scan input. So this is going to clock. So you can just take two patterns. So two patterns you can just take. And like 0, 1, 1 and 1, 0, 1. You can just tell like what will happen during shift phase, what will happen during capture phase. Like that just you can explain this diagram. So you can try it out now. What will happen during shift phase? What will happen during capture phase? how the patterns will be shifted. Like you can just draw a tabular column like this. Like say for example, clock pulse, and what will be the value in flip-flop 1, then flip-flop 2, flip-flop 3, and then scan out. So this flip-flop 3 output is only going to scan out. This is going to scan out. This is connected to top level scanning.
ನಿಂದ ಆಧಾರ್ ಕಾರ್ಡ್ ಬೇರೆದೈತಾ?
Hello, ma'am.
Yes, Rahul. You
Yeah,
can show
ma'am.
in your camera. Yeah.
No, ma'am. Once I will explain, ma'am, I am confusing with capture and shift.
Yeah. Okay. 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 So in your scan chain, just a minute. Yeah, I'm already sharing my screen, right? So in your scan waveform, how it will be there? First, you will be, this is your scan enable. So first we will be having shift phase. Like first you will be having this load unload phase, that when EDT comes, in order to reset the LFSR flops, you'll be having that load unload phase. Load unload. And then next we have the shift phase. Next we have the shift phase. And then you have the capture phase. You have the capture phase. And here again you have the same load and load phase, and then the shift phase. Load and load, and then next is the shift phase. So now here if you see first the clock pulse.
Ma'am, you are
Pulse.
sharing the screen, ma'am.
Okay, just a minute. Yes, I'm sharing the screen with you. Is it visible now?
No, ma'am. It is just previous screen only visible. Previous you have drawn empty tables. No?
ಯಾವ ಬಂದೆ? ಏನಪ್ಪ ಎಲ್ಗೂ ಇದ್ರೆ?
Okay, just 1 minute. I'll just connect to other net.
Yeah, okay.
Okay, I'll just leave this session and join once again. I'm connected to other network, but still I think it's not visible. So just a minute, I'll just join again.
Yeah, okay.
Okay, is my screen visible now? Is my screen visible?
Yeah, ma'am. Yeah, now it is.
Okay. So this is how you'll be having the scan chain waveform. So first we have the shift phase. So clock pulse and then flip-flop 1, flip-flop 2, and then flip-flop 3. And you have your scan out. So first clock pulse. First clock pulse, what will happen? The first pattern's LSB bit. This first pattern's LSB bit will go into flip-flop 1. So this first pattern's LSB bit will go into flip-flop 1. So here you will be having this flip-flop. Flip-flop 1 will be having 1. And then during the second pulse, what will happen? This value would have got shifted here, and here the second bit of the pattern, that is this one, it will go into flip-flop 1 like this. So first this, just like this one. So if you're having a shift register like this, so if you're going to load a pattern like 0 1 1, so first pulse here 0 would have come. Next time what will happen? Sorry, 1 would have come. Next time this one will get shifted here and this one will come here. Next time what will happen? This one will come here, this one will come here, and this 0 will come here. So that is the operation which is happening. So here this one will come here, next one will be here. And during the third pulse, this one will come here, this one will come here. So this one is coming here, this one is coming here, and that 0. This 0 that is going here. So flip-flop 3's output is only connected to scan out. So flip-flop 3's output is only scan out. So here it will be 1. So till this time your scan enable would have been 1. Scan
Okay.
enable is 1. So this is
Okay.
like loading. Yeah. This is your loading of first pattern. Loading of first pattern. So next is you'll be having your capture phase. So this is like in your fourth pulse. So here scan enable will be equal to 0. So capture phase, what will happen? Whatever value is there at the D input of the flops, that will be captured into the flop. So as of now, what is stored into this flop as per the last shift? 0 1 1 is stored. So now here what will happen is this one, through this NOT gate, it would have come and stayed here at the D input of this flop. And this 0, through this NOT gate, it would have come and it would have stayed here at the D input of this flop. And the D input of this flop, so like it will be coming from one primary input. Primary input will be coming from a primary input. So like during DFT time, like if we'll just assume it to be X. This primary input will just assume it to be X, either it is 0 or 1.
Okay, ma'am.
Now what will happen is, so we'll just assume that to be X. Okay. So
Yeah,
now whatever value is there in the D into the top,
ma'am.
0 will get
Ma'am,
captured into flip-flop 3.
ma'am, in
Uh,
flop 2, it is 1, right?
yeah.
Yeah, 1, right? Okay.
Flop 2, yeah, flop 2, which is 1. Yes, yes, correct. So flop 2, here 1 will come, and here we'll consider that to be X. So here scan out, whatever is there in the flip-flop 3 only, it is going. So this is the capture phase. And next again, you have the shift out phase. So fifth pulse, what will happen is, old pattern will be unloaded and new pattern will start to load. So here old pattern will get unloaded, unloading of old pattern and loading of new pattern will happen. So here what will happen is, whatever value was there here, that will come here. So flip-flop 3 output is only connected to scan out. So scan out also will be 1. Here whatever value was there, that will come here. Here the LSB bit of the second pattern will come. So that is 1. This 1 will come here. And then sixth pulse, during the sixth pulse, this value will come here. This value will come here. And the next bit, the middle bit of the second pattern, that is the 0. The 0 will come here. So here scan out, a flip-flop 3 output is only connected to scan out, so it will be X. And seventh pulse, it will be like this value will come here, this value will come here. Here this bit, this MSB bit of the second pattern, this first pattern will come. Here flip-flop 3's output is only connected to scan out, so here it will be 1. So this is like unloading old pattern, unloading old pattern, and loading new pattern. So in this, if they ask like explain scan chain operation, then just theoretically you can explain what will happen during shift phase and capture phase. If they ask you to explain with the help of an example, then you can like take two patterns like this, take a small combo logic circuit and just explain like this, what will happen during the shift phase and capture phase. If they ask with example, just if they ask like explain scan chain operation, then just as you had said previously, you can just tell what will happen during shift phase and what will happen during capture phase. Okay.
Okay.
Okay. So next question is, so you consider this scenario. You're having one ICG here. ICG. And this is like functional enable. And then, okay, let me just draw it a little bit. This is the ICG. This is functional enable and test enable is actually, or this is functional enable. This is test enable. Functional enable, it is coming from some combo logic. Test enable, just assume that it is grounded. And then here you have the latch. And you are having this clock. ICG's output is only going to the rest of the flops. So this clock will be coming from an OCC output. So based on fast capture mode and scan enable, it will be like PLL. One clock is PLL, other clock is scan clock. So in this case, you will get a clock controllability DRC. So how can you actually fix this DRC?
Ma'am, by adding lockup latch, by adding delay.
No, actually, can you think of some other possibility?
Okay. Ma'am, what years you will get, ma'am?
Proper clock is not getting propagated to the flops. You can analyze this ICG and you can tell what can be the fix.
Okay. Ma'am, by adding mux,
Where will you add a mux?
ma'am, between clock and AND gate, clock input and AND gate.
Okay, here you are telling.
No, ma'am,
Your
no, ma'am. There is a input, no, ma'am. For AND gate, clock is given as input, no, for AND gate.
this complete structure is an ICG. So this
Yeah,
is an integrated clock gating cell.
yeah,
Complete structure.
okay. Ma'am, by connecting fast clock to the mux, means we should add the mux for to OCC clock port and fast clock. We should connect to the mux.
Where can you exactly tell me the point?
Ma'am, after OCC, ma'am, after OCC generating the clock pin is there, no? Yeah, there only.
Mm.
Yeah, if you add mux, we should connect that OCC clock pin to 0 and fast clock to 1.
Okay. So, and select line, we are tying it to test mode signal.
Yeah, ma'am.
Okay. So actually to this ICG, OCC's output only has to get propagated.
Yeah.
So what is the fix? What you have to do is, so here what is the problem is, here if you see, test enable is actually tied to ground. This is the test enable signal. So it is tied to ground. So if if this OR gate, it is like OR gate input, it is tied to ground means, say now it completely depends upon functional enable. Just assume that the functional enable is also 0. So if the functional enable is also 0, here you are getting 0. So here if it is 0, the output of this latch also will be 0. So what will happen? It will become 0 completely. This output of this ICG will become 0. So in scenarios like this, proper clock will not get propagated to the flops. In scenarios like this,
Okay.
proper clock is not getting propagated to the flops. Proper clock is not getting propagated to the flops. So the fix which you have to do is, you have to do is, you have to just remove this ground and then tie the test enable signal either to test mode or else you can tie it to scan enable signal. Okay, you can either tie it to test mode signal or else you can tie it to scan enable signal. So this is how you can fix this issue. Whenever you have ICG, the test enable signal, you can either tie it to the test mode signal or scan enable signal.
Ma'am, it was grounded now, ma'am. You can remove ground and you can tie it to test mode, ma'am.
Yes, correct. Yes,
Means
you can tie it to test mode.
how to change that grounded connection, ma'am?
In place of ground, one tick B0 if it is there, right? That ground connection. So test.te, one tick B0 is there means remove it and tie it to test mode signal.
Okay, ma'am. Okay.
And next question is, here you can either tie it to test mode or scan enable signal, right? So which
Yeah,
is more advantageous and why? Tying the test mode to tying the test enable to test mode is more advantageous or scan enable is more advantageous?
ma'am, scan enable, I think it is more advantageous.
Yes, correct. So can you tell like why tying it to scan enable is more advantageous?
Yeah, ma'am. If we make scannable, if we make scan enable one, we can directly select. Means what is scan input, ma'am?
Okay, so I'll tell you the reason. So in this case, right, if you suppose, just imagine that you have tied it to test mode signal. You have tied it to test mode signal. And now what will happen is test mode, it will be completely one throughout DFT. So test mode will be one throughout DFT. So what will happen? This test enable of this ICG will become one. And here the output of this OR gate also is just one. It will always be one. So what will happen? Output of this OR gate is one. So the latches output is also one. So here you will be having this clock. We'll just assume that this clock name is clock. So here you will be getting the clock and this clock will be continuously propagated to the floor. So here what is happening is throughout DFT, test mode is 1. So therefore what is happening is tool will be able to detect stuck at zero fault. Tool will be able to detect only stuck at zero fault on test enable net, because test mode is always 1. So only stuck at 0 it can detect on this test enable net. Okay, in order to detect stuck at 1, the tool has to try to put a 0 value in this net. So here the tool can only put, so the test mode is always 1.
Yeah, okay, ma'am.
Yeah. So here test mode is always 1. So only stuck at 0 can be detected on the test enable net. And the faults on the functional enable and the faults on the functional enable net will be blocked. Why? Because test mode is always 1. So the output of the OR gate will always be 1. If there are any faults in this functional enable net, that is getting blocked, that is not getting detected. Okay. Therefore, tying or fixing the above error, by connecting test enable of ICG to scan enable is more advantageous. is more advantageous. So now we will see how. This is the ICG. So now here I will tie it to scan enable. So here what will happen? We will consider what will happen during shift phase and what will happen during capture phase. So first is during shift phase. During shift phase, scan enable is going to be 1. During shift phase, scan enable will be 1. So here this test enable is also 1 because it is connected to scan enable. Output of the flop will be equal to 1. Output of this OR gate is 1. Output of this latch will also be equal to 1. And here you are having this clock. So this clock will be propagated to the flops. So during shift, what is happening? Always clock will be propagated to the flops. Always clock will be propagated to the flops. Propagated to the flops. Okay. So and stuck at 0 on test enable of ICG is also detected. ICG can also be detected. Now if you consider capture phase, so here it is like connected to scan enable, right? Scan enable will be equal to 0. So this will become 0. So it is like this during your capture phase. So now what the tool will do is during capture phase, there are two conditions. One is if the tool, during capture phase, what is happening? Stuck at 1 on test enable of ICG is detected. Because scan enable is 0 now. So scan enable is only tied to the test enable of ICG. So stuck at 1 on test enable of ICG is detected. And now here there are two possible cases. One thing is like if the tool wants to detect stuck at 0 on functional enable. If the tool wants now in this functional enable, the faults on the functional enable can be detected. So if the tool wants to detect stuck at 0 on functional enable, I'll just consider one flop for simplicity. So if the tool wants to detect stuck at 0 on functional enable, then the tool is capable of writing a pattern like this. It will try to bring a 1 value here. So what will happen? This OR gate output will become 1 and the latches output will also be 1. So this clock is there and this clock will be propagated. So which means clock is pulsed for this flop. Clock will be pulsed for this clock. So good machine simulation. So this you just assume it as scan flop A. So the scan flop A will capture new value at its D pin. New value, that is nothing but value at its D pin. Because clock is getting pulsed. But if you consider faulty machine, then what will happen? So faulty machine means the tool would have induced a stuck at 0 fault here. The tool would have induced a stuck at 0 fault here. So in order to detect functional enable, stuck at 0 on functional enable. So as it is stuck at 0, even though as it is like stuck at 0, this value will be 0. So here it will be 0, latch output will be 0. So this way, for simplicity, I'm just considering one flop. This is scan flop A. So here also it will be 0. So what is happening? Clock is not pulsed. Clock is not pulsed. So faulty machine, what is happening? For faulty machine, scan flop A will hold its old value. Old value, that is its last shifted value. Last shifted value. Okay, so in this way, because clock is not getting pulsed. So in this way, stuck at 0 on functional enable can be detected. Same way, if you want to detect stuck at 1 on functional enable, to detect stuck at 1 on functional enable. So here it will be like this. So good machine simulation, what will happen? So if you assume a fault, get the opposite value. So the tool will try to put the opposite value only. Stuck at 1 means the tool will try to put a 0 value. Previously, yeah, okay. Tool will try to put a 0 value. So here it is 0. Output of this latch will be 0. So here output of this AND gate will also be 0. So this, for simplicity, I'm just considering one flop. This is scan flop 1. So here what is happening? Clock is not pulsed. Here in this case, clock is not pulsed. So what will happen? Good machine, scan flop A, I've just named it as scan flop A. So scan flop A will hold its last shifted value. Last shifted value. Scan flop A, it will hold its last shifted value. Whereas now if you consider faulty machine simulation. So if you consider faulty machine simulation, now the tool would have induced the fault in it because it is a faulty machine. The tool would have induced a fault. So what fault we are assuming? Stuck at 1, right? So the tool would have induced a stuck at 1 fault here. So as there is a stuck at 1 fault here it will be 1. The output of this OR gate will be 1. Here the output of this latch will be 1. And whatever value is there in the other input of the OR gate, AND gate, that is clock. So this clock will be propagated to the flops. This is scan flop A. So here what is happening? Clock is pulsed. In faulty machine, clock is pulsed now. Clock is pulsed. Therefore, scan flop A will capture new value. That is nothing but value at its depth. So good value and faulty value in this way. So in order to detect the faults in the functional enable, the tool will do like this. Okay. But if you tie it to test enable signal, you cannot detect the faults which is there in the functional enable, and also like stuck at 1 on test enable of the ICG cannot be detected. So that is why tying the test enable of ICG to scan enable is more advantageous than tying it to the test mode signal. So this was my next question.
Yeah, okay.
Okay. So we will be declaring like reset as a clock during our lab sessions, right? Instead of pin constraints. So what is the advantage of declaring the reset as a clock instead of pin constraint?
Yeah, ma'am, I am not sure about that.
Okay. Um, so advantage of declaring reset as a clock. You can mute yourself. Okay. So say for example, you are having a flop like this in the design. This is the reset port. Just consider that this is an active low reset. So this is the reset port name, RECT. So if we declare like this, add pin constraints, constraint to one, reset. Okay, add pin constraint to one, reset. So if we declare like this, then what will happen is always reset. This reset will be 1. Always reset will be 1. Always in the sense during shift and capture phase. During shift phase and capture phase. So now what is happening? So always this reset net is 1. So tool will be able to detect only stuck at stuck at 0 on reset net, because it is always 1. So reset net is always 1. So tool will be able to detect only stuck at 0 on the reset net. The same thing, if you use it as a clock, if you declare the reset as a clock, add clocks, off state is 1, reset. If you do it like this, then the decision is with the tool, whether to make it 0 or 1, the decision is actually with the tool. Decision is with the tool. So what the tool will do is, during shift phase, reset will be equal to 1. It will keep the reset as 1, that is off state. In this example, I've considered an active low reset. Okay, so it's off state. It will keep, because during shift phase, reset should not become 0. If reset becomes 0, then shifting everything, the output of the flop will become 0, and whatever value we are shifting, that will not get reflected. Only the output of the flop will become 0. So during shift phase, reset should not be pulse. Reset has to be in its off state. During capture phase, now the tool can decide. During capture phase, the tool will decide. So if it wants to detect stuck at 0 fault, then what the tool will do is good machine, faulty machine, it is considering. So stuck at 0 means assume a fault, that is stuck at 0, force a opposite value. So we'll just consider like this. This is D, this is Q, and this is reset. So assume a fault, that is stuck at 0, it is going to detect. So give a opposite value according to D algorithm. So the tool will apply a opposite value here. And now the tool will try to write a value like this 1 here. Okay. So now what the tool will do is, here Q, as reset is not pulsed for this particular flop, Q will be equal to D. So D is nothing but 1 here. Okay, this is like whatever value is there in the D input, that is becoming 1. This is good machine. Now faulty machine, what the tool will do? Faulty machine. So faulty machine means the tool would have induced a fault. So this is D, this is Q, this is reset, Okay. So now the tool has induced this fault. Now the tool has induced this stuck at zero fault. So if the tool has induced this stuck at zero fault, then what will happen? Here, like the tool has induced this fault, stuck at zero fault, it has induced. So the value here will be 0. So 0, reset is pulsed for this flop. So output of this flop will become 0. So good machine value is 1. Good machine value is, good machine output is 1. Okay. Faulty machine output is, faulty machine output is 0. Okay. So what is happening? Therefore, stuck at 0. Stuck at 0 is detected on reset net. Next, if it wants to detect stuck at 1, to detect stuck at 1, stuck at 1 fault. So this is D, this is Q. This is the reset, active low reset. So stuck at 1, assume a fault, give a opposite value. So the tool will put 1 value here, and here we'll just assume like at the D input 1 is there. So what is happening? Sorry, assume a fault, force opposite value. Here the tool will write 0. This is like good machine. This is good machine. So Q will be equal to, as reset is pulsed, Q is becoming 0. Whereas faulty machine, the tool has induced a stuck at 1 fault here. So the tool has induced a stuck at 1 fault. So here this will be 1. So what will happen? We'll just assume like here it is 1. So reset is not pulsed. So here in this case, Q will be equal to D. That is Q will be equal to 1 because at the D input 1 is there. So good machine value here is, good machine output is 0. And faulty machine output is, 1. So what is happening? Stuck at 1 is because good machine is not equal to faulty machine. Good machine output not equal to faulty machine output means fault gets detected, right? According to fault simulation. So good machine output is not equal to faulty machine output. Therefore, stuck at 1 fault is detected on reset net. So that is why in order to detect the faults, in order to detect all the faults on the reset net, we are declaring, that is in order to gain a higher coverage, we are declaring the reset as a clock instead of pin constraint. Okay. Okay.
Okay.
Next question is, what is feedback loop DRC and how can you fix it?
ಈಗ ನನಗೆ ಮಾಹಿತಿ ಪ್ರಕಾರ ಯಾರೋ ಒಬ್ರು ಏನೋ ಒಂದು
You can like draw it and then later you can show it. You can show it in your camera. Feedback loop DRC and how you can fix it.
ಅಲ್ಲಿದ್ದಾಗ ನನಗೆ
Hello, ma'am.
Yes, Rahul.
Yeah, ma'am. Can you only explain, ma'am? I can't able to explain properly.
Okay.
ಆಕ್ಸಿಡೆಂಟ್ ಆಗಿತ್ತು ಅದ್ರ ಒಳಗೀಗ ಅವತ್ತಿಂದ ಇವತ್ತುವರೆಗೆ ಮಾಡಿದ್ರು ಒಂದು ಮಾಡಿದ್ರು ರಿಟರ್ನ್
So, say for example, you are having some combinational feedback like this. So, say for example, this is A, this is B, this is C. So, in this case, if you consider this pattern in this case, A, B, C, and then output P. So, if you consider this pattern 1, 0, 1, then the output will always be toggle. So, you can explain with the help of an example like this. So, if it is 1, 0, 1, and we will first assume that this is just first assumption, assume that P is 0. Now, what is happening? This one, this 0, it is actually, okay. This 0, it is actually coming here. So 0 and with 1 will be 0. Here 0 and with 1 is 0. 0 and 0 both are 0 or 0 is 0, but it is a NOR. So here it will be 1. So now what is happening? P is changing to 1. P is changing to 1. So now what will happen? This will become 1. So 1 and with 1, the output of this one will become 1. This one will be 0 only. So 1 ORed with 0 will be 1, but it is a NOR gate here. So here it will be 0. Here it is like, this is 1, right? So 1 and with 0 will become 0 now. So here if you see continuously, it is toggling. Okay. So here in this case, because of the feedback, the output will be continuously oscillating. So what is the problem here is ATPG tool can't determine whether the net is 0 or 1, whether the net, that is P net, whether it is 0 or 1. So it will consider as X. So we will lose the coverage on the net. So what is the fix? The fix is, this is a combo logic. It is there like this. So what can we do is, the fix is, you can break the feedback loop. So here you can actually add a mux. So here feedback loop is there, right? So you can just break this feedback loop. Here you can add a mux. So 0th input, we will connect it here. 0th input is what the designer intended to give. And first input, we will tie it to some other nearby flop output of nearby flop. So select line will be tied to test mode signal. So when test mode is equal to 0, whatever designer intended to give, that is the feedback loop only will go. This previous output only will be given to the input of the combo logic. When test mode is equal to 1 DFT mode, some nearby flops output will be going as an input to the feedback loop. So we are just breaking the feedback loop. So this is what is a feedback loop DRC, and this is how you can fix it.
Yeah, okay. Yeah, ma'am, can you please share this video, ma'am, after this interview?
Yeah, you can ask Manohar sir. Sir will share it with you.
Okay, ma'am.
So next question is, so we consider an example like this. So there are two scan clocks, scan clock A and then scan clock B. So assume that scan clock A, it is going as a clock for 6 flops, which are positive edge triggered, and it is going to 3 flops. These 3 flops are negative edge triggered. Scan clock A, it is going as a clock to 6 flops, which are positive edge triggered, and it is going to 3 flops, which are negative edge triggered. And scan clock B, it is going to 3 flops that are positive edge triggered. So now I've given a command like this: insert test logic hyphen number 3. So how will the tool place the flops in the scan chain? Place the flops in the scan chain.
Hello, ma'am.
Yes, Rahul.
Yeah, ma'am. First, negative it's triggered for scan clock A is placed first, and afterwards, 6 positive it's triggered flops, and after then scan clock B is 3 flops.
These 3 negative edge triggered flops, it will place in it is placing first, then these
Yeah,
flops it is placing, and then these
yeah,
flops it is placing. Correct?
yeah, ma'am. Correct, ma'am.
Okay. So here if you see in this command, we have not given hyphen edge merge and hyphen clock merge. So in this command, we have not given hyphen edge merge and hyphen clock merge switch. Therefore, tool will not go for edge mixing and domain mixing. Tool will not go for edge mixing and domain mixing. So now tell me how it will place these flops.
Yeah, ma'am. This I don't know, ma'am.
Okay.
Hello, ma'am.
So if you
Okay.
have not if you have not given this hyphen edge merge and hyphen clock merge switch, then what the tool will do is tool will keep positive flops, positive and negative edge triggered flops in different scan chains. In different scan chains, and the tool will keep the flops with different scan clocks, different scan clocks in different chains, different chains. So how the tool will place it? So here if you see, the tool will place positive flops and negative flops in different scan chains, and the tool will place flops with different scan clocks into different chains. So totally, and we have given insert test logic hyphen number 3, which means 3 scan chains. 3 scan chains the tool has to place. So what will happen is it will keep 3 chains. So chain 1, chain 1, chain 2, and chain 3. So now what the tool will do is the tool will keep 6 flops, that is the positive edge triggered flops of scan clock A. And then in chain 2 it will place the 3 flops, that is negative edge triggered flops of scan clock A. And in third chain the tool will keep 3 flops, that is the positive edge triggered flops of scan clock B. So the tool will not mix the clocks with different scan clocks, and also the tool will not mix positive edge triggered flop and negative edge triggered flops. So the tool will place it in this way. Okay. So now the next question is, what is the problem? What is the problem which will arise in the above scenario? So what is the problem which will come in the above scenario?
Hello, ma'am.
Yes, Rahul.
Yeah, ma'am. I don't know. I think only domain mixing and clock mixing may happen, but you told the command will be not given. Yeah, and this I think I don't know what will happen.
Okay. So here if you see these chains in the above case, chains are unbalanced. Chains are unbalanced. Just 1 second, I'll just connect to my charger. 1 minute.
Okay.
ಒಳ್ಳೇದಾದ್ರೆ ನಮ್ಮ ಅವನಿಗೆ ಒಳ್ಳೇದಾಗುತ್ತೆ, ಇವ್ರಿಗೆ ಅನ್ಯಾಯ ಆಗೈತ, ಇವ್ರು ಆದ್ರೆ ಸರಿಪಡಿಸಿ ಅವನು ನೋಡಿರ್ಬೇಕು. ನಾವು ಅವನ್ ತೆಗೆದು ಇವ್ರಿಗೆ
Yeah. In the above case, right, chains are unbalanced. Unbalanced means like they are not having equal number of flops in the scan chain. So one scan chain is having 6 flops, other scan chains are having only 3 flops. So the above case, chains are actually unbalanced. So what problem will happen? So all scan chains will be operated parallelly. Will be operated parallelly. All the scan chains will be operated parallelly. So that means operated parallelly means shifting will happen. Shifting will happen for all scan chains at the same time. Once shifting is done, shifting is done for all scan chains, we have the capture. So here, if you see, I'll just give with an I'll just explain with an example what problem will come. So in chain one, what we are having? We are having 6 flops, that is positive edge triggered flops of scan clock key. So I'll just draw it here. This is what is there in chain one. One, two, three, 4, 5, 6. Okay. And in chain 2, what we are having? In chain 2, we are having 3 flops. That is negative edge triggered flops of scan clock key. Okay. And in chain 3, we are having 3 flops. That is the flops of scan clock. Okay, let me just draw it here. In chain 3, we are having 3 flops. That is of scan clock B. So here there are like 2 clocks, right? Scan clock A and scan clock B. Scan clock A and scan clock B. So when the first rising edge of scan clock A comes, when the first rising edge of scan clock A comes, what will happen? The data, instead of like numbers, I'm just representing it by alphabet. Okay, A1. This A1 data will come into this block. Okay, during the first rising edge of scan clock A. Now, during the rising edge of scan clock B, what will happen? This is clocked by scan clock B, right? This is clocked by scan clock B. So that data will come here. That is the LSB bit of the data will enter here. And during the falling edge of scan clock A, what will happen? This data will enter into this scan chain 2. This is what will happen. Next, again, you have this another pulse, second pulse. So in this case, what will happen? During the rising edge of scan clock A, this positive edge. So this data will come here. Here the next next data will come here. During the rising edge of scan clock B, what will happen? This data will come here and the new data will come here. And during the falling edge of scan clock B, this data will come here and here the new data will come. Okay. And next, during the third pulse. During the third pulse, what will happen? During the rising edge of this pulse, whatever data was there here, that will come here. Here, this B1 will come. Here, the new C1 will come. During the rising edge of this one, what will happen? This data will come here. Here, B3 will come. And here, C3 will come. Okay. And during the falling edge of scan clock A, what will happen? This data will come here. Here, B2 will come. Here, C2 will come. Now, next. During the next pulse. During this next pulse, during the rising edge of this one, what will happen? This data will come here. Then here this B1 will come. Here this C1 will come. And here this D1 would have come. Okay. So this is what will happen here. And for during the rising edge of scan clock B, no operation will happen because already the data has got shifted into the scan chain, 3 flops of the scan chain. And during the falling edge of this pulse, at that time also here also no change will happen because already the data has got shifted into the chain 2. And next pulse. Next pulse, what is happening? During this pulse. During this pulse. So during the rising edge of this pulse, what will happen? This data will come here. Here B1 will come. Here C1 will come. Here D1 will come. Here E1 will come. Okay. And during the rising edge of scan clock B, nothing will happen because data has already got shifted into scan chain 3. And during falling edge of scan clock A also, nothing will happen because data has already got shifted. Now, during this pulse, during the 6th pulse. So what will happen? During the 6th pulse, during the rising edge of the 6th pulse, what will happen? This A1 will come here. Here this B1 will come. This C1 will come. And here this D1 will come. Here this E1 will come. And here this F1 will come. So that is what is happening. So here if you just see, these are 2 clocks. These are 2 clocks coming at the same time window. So this is nothing but 2 clocks. 2 clocks, they are coming at the same time window. Same time window. So this is actually equivalent to 1 pulse. This is equivalent to 1 pulse. Okay. So this is nothing but the first pulse. This is the second pulse. This is the third pulse. This is the fourth pulse. This is the fifth pulse. And this is the 6th pulse. So here what is happening is, totally in the above example, we require 6 clock pulses. 6 clock pulses are required for shifting. Totally in the above example, 6 clock pulses. 6 clock pulses are required as shifting is done parallelly. Shifting is done parallelly for all scan chains. So for scan chain 2 and 3, for chain 2 and chain 3, so in the last 3 pulses, right, in the 4th pulse, 5th pulse and 6th pulse, no shift was happening. Okay, for chain 2 and 3, in the last 3 pulses, no shift was happening. No shift was happening. So what was happening? It was just retaining its previous data because already 3-bit data has to be shifted. It has already got shifted into this, scan chains. So it was just retaining its previous data. It was just retaining its previous data. So that fourth pulse, fifth pulse, and sixth pulse, right? 4, 5, and 6, they are nothing but the dummy cycles. Dummy cycles for chain 2 and chain 3. So whenever you have unbalanced chains, you will have dummy cycles. And if you have dummy cycles, then the test time will actually increase. So test time formula is nothing but number of patterns into number of shift cycles per pattern into clock period of scan clock. So what will happen if number of shift cycles increases? If it increases, then test time also increases. Okay, so number of dummy cycles. So if you have unbalanced chain, you will have dummy cycles. If you have dummy cycles, the number of shift cycles are actually increasing. So test time also increases. Okay, so test time it increases. So now the fixes solution is go for edge mixing and domain mixing. Go for edge mixing and domain mixing. To get balanced chains. So this is where we will actually give that command. So if you give a command like this now, insert test logic hyphen number 3 hyphen edge merge hyphen clock merge. So now it will allow for edge mixing and domain mixing. So now what will happen? Like here also it will keep 3 chains. So in chain 1, so we what we were having in our example, we are having like scan clock A, it is going as 6 flops which are positive edge triggered and 3 flops which are negative edge triggered. Then scan clock B, it was going to 3 flops which are positive edge triggered. So this is what we were having. This is the scenario. So now what will happen in chain 1? In chain 1, as we have gone for edge mixing, what the tool will do is, so here also 3 chains, insert test logic hyphen number 3. So 3 chains that it will be having, chain 1, chain 2, and chain 3. So in chain 1, the tool will keep like 4 flops, that is positive edge triggered, 4 positive edge triggered flops of scan clock A. And then in chain 2, what the tool will keep is 3 flops, that is the negative edge triggered flops of scan clock A. And here the tool will keep like 3 flops, that is the positive edge triggered flops of scan clock B. And here only 4 flops is there, right? Total 6 flops are there. So it will keep 1 flop, that is positive edge triggered of scan clock A. It will divide it. 4 flops it has kept here. Here it will just divide it. And then 1 flop, that is positive edge triggered of scan clock A. Okay, so this is how the tool will place. Okay, so now here if you see, as scan chains are operated parallelly, how many shift cycles will happen? Shifting will happen parallelly. Shifting is done parallelly. Now in this case, how many clock pulses are required for shifting? Total number of clock pulses required for shift is 4. because in all the scan chains, 4 flops are only there. Total 4 flops are there. So total number of clock pulses required for shift will be equal to 4. So what is happening after balancing? After balancing, number of clock cycles, number of clock pulses required for shift decreases. So therefore, test time will also decrease. Okay, so hence we are going for edge mixing and domain mixing. So in this formula, if you see, if number of shift cycles per pattern decreases, test time will also decrease. Okay.
Yeah, okay.
One second. Okay. Um, okay. So consider this example. So consider this example. So what are all the faults will get detected and what are all the faults will not get detected? What faults? This we consider it as A net, B net and Y net. What faults will get detected and what faults will not get detected? What faults will not get detected? So you can just try it out and you can tell me your answer.
Ma'am, at BNet, stuck at 0 is detected and stuck at 1 is not detected. At A, stuck at
One second, I just write it down. B, what is detected?
yeah, ma'am, stuck at 0. Stuck
Okay.
at 0 will be detected.
Okay. Then?
Yeah, ma'am, at stuck at 1 will be not detected.
Okay.
In net A, stuck at yeah, both stuck at 1 and stuck at 0 will be not detected.
Yes, correct. Okay.
Yeah, at Y, stuck at 0. Yes,
Stuck at
stuck
0
at
is
0 will be not detected, I think. No?
yes, correct.
Yeah, stuck at 1 will be detected.
Yes. So here answer is only B stuck at 1 and Y stuck at 1 will be detected. So can you just tell me like how you arrived at this answer? Any one example you can just take and tell me how you arrived at this answer.
Yeah, ma'am, as B is tied to ground means the value will be 0, then the good value will be also 0 and 0 faulty value will also be 0. So in at Y, stuck at 0 will be not detected, only stuck at 1 can be detected.
So here this is like B is tied to ground. This is B, this is A. This will be coming from some scan flop output. And this is Y. So B now if we just consider B stuck at 0. If we just consider like B stuck at 0, then just a minute. B stuck at 0. If we consider, so this is like A, this is A, this is B. This is coming from one scan flop, and this output Y is going to another scan flop. So stuck at 0 means assume a fault. So B stuck at 0, assume a fault has happened. force the opposite value. So the tool will try to force the opposite value on this. So good machine, this is good machine. Tool will try to force the opposite value on this particular B net, but the tool cannot make it. That is, the tool will try to make it as 1, but the tool is not able to make it because it is already tied to 0. So here it has to put 0 only. Then here it will, in A net, it will try to write a value. It will try to write a value in such a way that this value will get, this faulty value will get propagated to the output. So here what is happening, here it will write 1. So good machine, here it will be 1. So the same thing during capture phase, this will get captured. If you consider faulty machine, then what will happen? So the tool will induce a stuck at 0 fault here. The tool will induce a stuck at 0 fault. But as here already it is like the tool will induce a stuck at 0 fault. So here it will be 0 only. Here the tool will try to write a 1 value. So here it will be 1. This value only will be captured into the flop. So good value is 0. Faulty value is 0. Faulty value is 0. So good value same as faulty value. So fault is not getting detected. Good value equal to faulty value. Faulty value. Therefore, B stuck at 0 is not detected. B stuck at 0 is not detected. And if you consider B stuck at 1, B stuck at 1 if you consider, so this is good value. This is A, this is B, and this is Y. So assume a fault, A stuck at B stuck at 1, force opposite value, the tool will try to put a 0 value. Already it is 0, so this is fine. Here the tool will write a pattern write a value in order to propagate this fault to the output. Here it will be 0. So this one only will be captured during the capture phase. Faulty machine, what will happen? Faulty machine is, so here you are having A, B, and this is Y. So here the tool will induce a stuck at 1 fault. The tool will induce a stuck at 1 fault. This will be 1. Here 1 value is written. 1 and 1 will be 1. This will only be captured. So good value here is 0. Good value is 0. Faulty value is 1. Faulty value is 1. Therefore, B stuck at 1 is detected. So in the same way, you can do it for other cases. Okay, so these two faults will get detected. Others are not detected. B stuck at 1 and B stuck at 1 and Y stuck at 1 is detected. Others are not detected.
Yeah, okay.
Okay. So next question is, how will you take care of synchronous reset flop in your design?
What, ma'am?
How will you take care of synchronous reset flop in the design?
Ma'am, I'm not sure about that experiment.
Okay. So synchronous reset flop. What are synchronous reset flop? So synchronous reset flop means reset can be applied anywhere. Can be applied anywhere. But its effect is only at the clock edge. Only at the clock edge. So this is what is a synchronous reset flop. So reset can occur anywhere. Reset can be applied anywhere, but its effect is only at the clock edge. So the structure of synchronous reset flop will be like this. This is clock. This is the D input. And here you are having D. And here you are having reset. This is how the structure of synchronous reset flop will be there. So for synchronous reset flop, there is no separate pin for reset. There is no separate pin for reset. So it will not affect the state of flop during shift. Okay, so here if you see reset, it is ANDed with the input and it is given to the D pin. For asynchronous reset flop, you will be having a separate pin for reset. But for synchronous reset flop, the structure will be like this. The reset will be ANDed with the input and it will be given to the D pin. So as if we are not having, so what will happen is, it will not affect the state of the flop during shift because reset is ANDed with D and it is going to the D input. So it will not affect the state of the flop during shift phase. Okay. So there is no need for DFT engineer to make any changes. Therefore, there is no need for DFT team to make any change. Okay, asynchronous reset flop means you will be having a separate reset port like this. So if reset is pulse, it will be coming from some combo logic, or if it is coming from some other flops output, then we have to add the mux and correct it accordingly. That is for asynchronous reset because separate reset port is there. So if it is controlled by some combo logic, then the output, suppose if the output of the combo logic becomes 0, then what will happen? Output of this flop will become 0, so proper value will not get shifted. So that's why only we used to add a mux like this, and this will be connected to top level scan reset. This is test mode, everything will be done. That is for asynchronous reset flop. But synchronous reset flop, it is not having a separate reset port. Reset, it will be ANDed with D and it will be ANDed with the input and it will be given to the D pin. So it will not affect the state of the flop during shift. Even if reset is pulsed or something happens, it is not going to affect the state of the flop during shift because D input is ANDed with reset and it is given to the D input only. So that's why there is no need for DFT team to make any change.
Yeah, okay, ma'am.
Okay. So next is, you can take one AND gate and you can tell what are all the patterns which will detect all the transition faults in an AND gate.
At which net,
So you
ma'am?
can take all nets. AND gate, you can tell what pattern or which patterns will detect all transition faults. All transition faults. So this pattern, it will detect A is slow to rise. This pattern will detect B is slow to rise. Like that you can tell.
Okay.
Or I'll just give you few patterns. Which patterns will detect A is slow to rise, B is slow to fall, and Y slow to rise fault. Okay, A slow to rise, B slow to fall, and Y slow to rise fault. Which patterns will detect? A slow to rise, B slow to fall, and Y slow to rise.
Hello, ma'am.
Yes, Rahul.
Yeah, ma'am. At net A, 0, 0 and 0, 1, we can detect slow to rise.
1 minute, 1 minute. Slow to rise.
0, 0 and 0, 1.
0, 0 and 0, 1. This is A and this is B. Okay. This is for A slow to rise. Okay, so for B slow to fall.
Ma'am, for B, 0, 1 and 1, 1.
Slow to fall. 0, 1 and 1, 1. Okay. Then Y slow to rise.
Y slow to rise. Ma'am, 0, 0, 0, 1, 1, 0.
0, 0.
0, 1 and 1, 0.
How are you?
What, ma'am?
Is this what you have told?
Yeah,
Okay.
ma'am.
Can
Yeah.
you just like explain using paint, like how you have arrived at it? Any one fault you can just tell. I'll make you as a presenter. You can
Yeah,
explain
okay.
using paint, like how you have arrived at it. A slow to rise, you can tell. You have told 0, 0 and 0, 1, right? So how you have arrived at it, you can tell.
Yeah, okay. Hello, ma'am.
Yes, Rahul.
Is it visible, ma'am?
Yes, it is visible. If you can explain.
Yeah, ma'am. First, we have to consider one at the output value because we are doing slow to rise. Yeah, in order to detect slow to rise fault, now at point at net A we have to give first 0 and at second it means at B net we can give 0 first pattern, and second pattern first we can give 0 means 0 is fixed pattern, and next for B we can give 1.
A slow to rise we are going to detect, right?
Yeah, ma'am. Slow to
For
rise.
A slow to rise.
Yeah.
Okay, so first A slow to rise. Okay. Tell me once again.
Yeah, ma'am. For A slow to rise, we have to give first pattern. We have to give 0 for A and 0 for B.
Okay.
And second pattern we can we can give 0 for A and 1 for B.
Then we are detecting slow to rise for B net. We are not detecting it for A net because in A net we are not bringing the transition at all. A net is always 0, right? So the same
Okay.
thing, whatever you have said is correct, but it should have been done for B net. Okay. So
Okay.
I'll just share my screen once and
Yeah.
I'll
Okay.
just. So A slow to rise means A slow to rise. So what will happen here is, okay, so in your TDF, how it will be there? This is your scan enable. So shift to face, you'll be having like this. So here you'll just consider this as A pulse, and then just consider this to be B pulse and C pulse. B pulse and this pulse is C pulse. Two fast clock pulses are there. Okay. So now during A pulse, so if it is like to detect slow to rise, A slow to rise. So what the tool will do is, this is scan flop 1, this is scan flop 2, this is A, B, and this is Y. Scan flop 3. So here in this case, what will happen? First, the tool will try to write 0. The tool will try to bring a 0 to 1 transition in net A. So at the last shifted value, here this will be 0. Here the tool will be writing 1 in order to propagate this fault to the output. So here it will be 0. So during like B pulse, next during B pulse, what will happen? This is scan flop 1. Okay. And this is scan flop 2. This is B. and this is scan flop 3. So this B pulse is coming during the capture phase. So this 0 will get captured here. Next, what the tool will write is, the tool will try to bring a, the tool will try to write here a 1 value. It is bringing a transition, right? And it is trying to propagate this transition. So what will happen? If this net is free, if there is no A stuck at 1 fault, A slow to rise fault, if it is not there, then here it would have quickly changed to 1. This will be 1 only, so good value will be 1. If there is A slow to rise fault, so it will be 0. It wouldn't, within that time period, it wouldn't have got changed to 0. So this problem, it can either be in net A or in scan flop 1, anywhere. So because of that, this net hasn't got transitioned to 0. So it is, hasn't got transition to 1. So it is retaining its previous value 0. Here and on it will be the same. So this one, faulty value will be 0, 0 and 1 will be 0. Now during C pulse, what has happened? This is scan flop 1. This is scan flop 2. This is A, this is P, and this is Y. This is scan flop 3. Okay. So now whatever is there in the D input, that it will capture. So if it is capturing 1, then there is no A slow to rise fault. This is a good value. This is good value. If it is capturing 0, then that is a faulty value. So this is how it happens. So how you can write it is, A slow to rise. A slow to rise means, so AB. So first pattern, it will try to write 0 in A net. It will try to bring a 0 to 1 transition in A net. So this is A value. So first pattern it will write 0, second pattern set it will write 1, and B net it will always try to propagate that value to the output side. So B will be always 1. So this is how you can detect the A slow to rise fault. And B slow to fall. B slow to fall fault means, so same way, what the tool will do, the tool will try to bring a fall transition in B net. So fall transition means first pattern it will try to write 1, second pattern it will try to write 0. Then A net it will try to write a value which will propagate the output. Okay. And the next is what fault I have given, Y slow to rise, right? Y slow to rise. Y slow to rise means, so first it will try to get a 0 value in Y. So 0 value, how it will get in Y? So A and B, it will make it as 0. Next time it will try to, or either it can write like this, or else 0, 1 will also bring a 0 value on Y, or 1, 0 can also bring a 0 value on Y. And then the next pattern, it will try to bring a Y value in Y, 1 value in Y. So if it has to bring, it has to make A and B as 1. So this is how you can determine the fault. Okay, in whichever net it wants to detect a rise transition or fall transition, it will try to bring that transition in that particular net. In the other net, it will try to propagate the value to the output. So this is how you can determine.
Yeah, okay, ma'am.
Okay. And okay, you consider a NOT gate. Consider NOT gate. Explain how IDDQ test will detect stuck on fault. stuck on fault in a NOT gate. Okay. Consider a NOT gate. Explain how IDDQ test will detect stuck on fault in a NOT gate.
Yeah, ma'am, I don't know about this one. You will explain.
Okay. So, what is basically a stuck on fault?
Stuck on, I don't know.
Okay. So, stuck on, yeah. Okay. So, stuck on means faulty transistor is always on because it is having some manufacturing defect. The faulty transistor will be always on. Okay. So, just a minute. I'll just paste a diagram. Just 1 minute. Yeah. So, stuck on fault means that faulty transistor will always be on. So, this is how, this is what is like, if you consider a NOT gate, you just consider that this NMOS is stuck on. Okay, NMOS is stuck on. So, basically, I'll just write it in note. So, PMOS, when will it be on? PMOS will be on when Vin is logic 0. PMOS will be on when Vin is logic 0. And NMOS, it will be on when Vin is logic 1. Okay. PMOS will be on when Vin is logic 0 and NMOS will be on when Vin is logic 1. So if you consider a good circuit, so if you consider a good circuit, that is, it is not having that NMOS stuck on fault. So this is what is, this is how this NOT gate looks like. This is V out, this is V in. This is like PMOS and this is NMOS. So assume that Vin is changing from 1 to 0. Okay, Vin input voltage, assume that it is changing from 1 to 0. So when Vin is changed from 5 volt, that is logic 1, to 0 volt, that is logic 0. So initially what will happen? Initially Vin is 1. So NMOS will be on and PMOS will be off. Okay, Vin is 1. So NMOS is on and PMOS is off. So initially NMOS will be on and PMOS will be off. PMOS will be off. Okay. Now, when input voltage is around 2.5 volt, when input voltage is around 2.5 volt, so it is nothing but VDD by 2, assuming that VDD is 5 volt. Assuming VDD is 5 volt. So what will happen at this time? Both NMOS and PMOS, they will be there in their saturation region. So you can refer to operations like the regions of operation of NMOS and PMOS. Then you'll be able to understand CMOS circuit. Regions of operation of a CMOS circuit, if you see, you'll be able to understand. So they will be proving with the help of formulas. They will be telling you how at this point, how when Vin is equal to VDD by 2, how at this point, at this time, both NMOS and PMOS, both NMOS and PMOS will be in their saturation region, will be in their saturation region. So what will happen is, so for a small amount of time, for a small amount of time, both NMOS and PMOS will be conducting. NMOS and PMOS will be conducting. And during this time, both NMOS and PMOS, it is like conducting, it is on. Both NMOS and PMOS are on when Vin is equal to VDD by 2. So what will happen? And during this time, current will flow from VDD to ground. Current will flow from VDD to ground. So there is a direct path. Both are on. So there is a direct path. Both are conducting. PMOS and NMOS both are conducting. So there is a direct path for current to flow from VDD to ground. So now what is happening? We are reducing. We are like from 1 to 0, we are decreasing. When it is 5 volt, then only, this is logic 1. So when it is at 5 volt, then only NMOS is on, PMOS is off. In between, during 2.5 volt, both are conducting. So there is a path for the current to flow from VDD to ground. Okay. But as Vin reaches 0 volt, that is logic 0. Now what will happen if it is logic 0? PMOS will be on and NMOS will be off. PMOS will be on, and NMOS will be off. So no current will flow from VDD to ground. Okay, why? Because now PMOS is on and NMOS is off. So direct path of current to flow from VDD to ground is not there. So it will not flow. But if NMOS is stuck on, okay. So then what will happen if NMOS is stuck on? So you are having like this is PMOS and this is NMOS. Due to some manufacturing defect, it is always on. Just 1 minute. Yeah, okay. Sorry. So here, if NMOS is stuck on, this is PMOS, this is NMOS. If NMOS is stuck on, imagine that this is stuck on. Because of some manufacturing defect, it is stuck on. Stuck on means faulty transistor will always be on. So what will happen now? This is Vin. So in this case, even when Vin has reached 0 volt, NMOS will be on. NMOS will be on because it is having fault because of stuck on fault. So what will happen? This will actually occur if there is some manufacturing defect. So what is happening? There is a resistive short here. So here the current will actually, again, even when Vin reaches 0 volt, there is a path for current to flow from VDD to ground. So this is like resistive short. This is resistive short. So there is a direct path of current. There is a direct path for the current to flow from VDD to ground. Hence, current will be flowing continuously even after waiting for some time. Hence, current will be flowing even after waiting for some time. Flowing continuously. Even after waiting for some time. So that is what is said here in this graph also. If you see, the summary is, so I'll just copy paste this graph once again. So what is a summary here? When input is changed from logic 1, that is 5 volt, to logic 0, that is 0 volt. What is happening? After transition, that is after some time, after the transition, after like 1 to 0, after the transition has happened, after the transition, 1 to 0 transition. Okay, after the transition, good circuit should consume no static current. But if the circuit has NMOS stuck on fault, we will observe high IDDQ current. So this is how we can detect stuck on faults. IDDQ current. Okay. So if there is no defect, then what is happening? Then first during the transition, that is when at that point when Vin was equal to VDD by 2, at that time current will be there. But afterwards, current will settle when there is no transition, when Vin reaches 0 volt. But if you have stuck on fault, then even after Vin reaches 0 volt, current will still be flowing. So this is what is a summary. So this is how stuck on faults can be detected. Okay. And with the same concept, you can try to tell this answer. Okay. Okay. So you can tell like this is a NAND gate. So how to construct a NAND gate? This is the CMOS structure of a NAND gate. This is A, B. And then this is A. And this is B. And this is Y. So how have we arrived at this? So this rule we have to follow. Dot and then plus. So if it is PMOS, if you have dot in the expression, then that means you have to connect it in parallel. Plus means you have to connect it in series. Then NMOS means it is just the opposite. Here you will have series and here you will have parallel. So NAND gate is nothing but Y is equal to A and B whole bar. So whole bar is there. So at the end, we are not going to add any NOT gate. If whole bar was not there, at the end, we will add the NOT gate. But here whole bar is there. So we are not adding any NOT gate at the end. And there is dot here. So PMOS will be connected in parallel. So PMOS is connected in parallel and NMOS is connected in series. So this is how we have arrived at the diagram. This is P1, P2, and then let me just consider like N1, N2. Now tell me, A is equal to 0. This is the pattern. A is equal to 0, B is equal to 1. Okay, A is equal to 0 and B is equal to 1. This pattern will detect which fault? Detect which fault? Whether it is like P1 stuck on or P2 stuck on or N1 stuck on or N2 stuck on. Which pattern will detect this? This pattern will detect which fault?
Yeah, hello, ma'am.
Yes, Rahul.
Yeah, sorry, ma'am, I didn't got properly. I'm not able to explain this. I have to read once, ma'am. Once again, I have to read this. I have to go through this.
Yeah, okay. So here I'll just tell you. Here if you see, let me just draw it once. Okay, I'll just copy it. Okay, so now A is equal to 0 and B is equal to 1 we are applying, right? A is equal to 0 we are applying, B is equal to 1. So in this case, which one will be on? So this will be on because PMOS will be on when Vin is equal to 0. And this one will be off because its input voltage is 1. Okay. And NMOS N1 will be off and N2 will be on. Okay. So now what actually we just consider that this is good machine. This is good machine. So what will happen? Through this path, basically Y will be charged. So Y will be charged to 1 through this path. Okay. So in order to detect a fault, so like for this particular pattern, if you have like direct path if you have a direct path for the current to flow from VDD to ground, then that particular fault will get detected by this pattern. So which fault it will actually detect is, so this faulty machine, it will actually detect N1 stuck on fault. N1 stuck on fault. So here if you see, assume that this N1 is stuck on. This is stuck on. So what we are applying, A is equal to 0 and B is equal to 1, right? A is equal to 0, B is equal to 1, A is equal to 0, B is equal to 1. So even though the input voltage is 0, as this N1 is stuck on, it will always be on. So what will happen? Through this path, so this P1 is on, because like PMOS, this is on basically. Why? Because input is 0. Okay, Vin is 0. So this is on and this is stuck on. Although input voltage is 0, as this is having a stuck on fault, this will always be on. And this is on because input voltage for this N2 is on. So here you are having a direct path for the current, current to flow from VDD to ground. So hence, what will happen? With this pattern, we are able to detect N1 stuck on fault. Okay. Okay. So I'll just ask 2 more questions.
Yeah.
Okay. Can you explain the logic? So logic that decides, only this logic is sufficient, that decides which clock will be propagated during shift and capture. Okay, I can just draw a diagram and you can try to explain. Which logic? The logic that decides which clock has to be propagated during shift and capture. Just that particular logic is sufficient.
Yeah, ma'am. Logic 1 decides shift and logic 0 decides capture, I think. Is it right, ma'am?
No, the circuit. Which circuit? So explain the circuit that decides which clock will be propagated during shift and which clock will be propagated during capture.
Yeah, ma'am, I'm not getting properly, ma'am.
During shift, slow clock will be propagating. During capture, for stuck at slow clock will propagate. For TDF, fast clock will propagate, right? So which logic will basically decide that? Can you explain that logic?
Yeah, ma'am, I'm not getting properly. Can you explain, ma'am, please?
Okay, yeah, I'll just take the diagram 1 second. If you remember in OCC, you will be having a block like this in OCC. So that is only the answer. Okay, OCC you will be having a big circuit, but there is one small block like this, right? This block only decides which clock will be propagated during shift and which clock will be propagated during capture. Okay, so here let me just assume this I'll just consider it as mux1 and this is mux2. So mux1 only, mux1, it decides whether clock is propagated for shift or whether clock is propagated for capture. Decides whether the clock is propagated during shift. Whether the clock is propagated for shift or whether it is propagated for capture. So the select line of this mux1 select line, it is coming from scan enable. So when scan enable is equal to 1, scan enable is equal to 1 means it is the shift phase. So during shift phase, what is happening? Scan enable is equal to 1. This is the scan clock. So scan enable is equal to 1. So what is getting propagated? Slow clock will be propagated. Okay, so during shift. So for both stuck at and TDF, during shift phase, slow frequency clock will be propagated. Slow frequency clock will be propagated. Okay. Now when scan enable is equal to 0, that is capture. So during capture, if it is stuck at, then slow frequency clock has to be propagated. If it is TDF, then fast frequency clock has to be propagated. So this will actually be decided by mux2, whatever I consider mux2. So this is decided by mux2.
Whether it is stuck at or whether it is TDF, like that it is deciding, no? Mux2.
Yes.
Yeah. Okay.
So during scan enable is equal to 0. So see here, from where it is 0th input of this mux1, it is connected to the output of this mux2. So which clock has to be propagated, that will be decided by this mux2. So now here if you see, this is mux2. So select line of mux2 is, its select line is fast capture mode, FCM, fast capture mode. So when FCM is equal to 0, when FCM is 0, then that is stuck at. So what will have to propagate? Slow frequency clock will have to propagate during capture also. So when FCM is 1, then that is TDF. So what will be propagating? Fast frequency clock will be propagated. So now how it is happening? When FCM is equal to 0, this is only the slow clock. When FCM is 0, so that means it is stuck at. So slow frequency clock will be propagated. When FCM is 1, then that is TDF. So when FCM is 1, then that is TDF. So what is propagating? TLL output. That is nothing but the fast frequency clock. Fast frequency clock. Okay. And this clock gator is there, right? Here you are having this clock gator. This clock gator circuit only will decide how many pulses have to propagate. So this will decide how many pulses have to be propagated during shift and capture. How many clock pulses will be propagated during capture. Will be propagated during capture. Okay, so this will be decided by this clock gator. How many clock pulses will be propagated during capture? Okay, so when it is like according to this diagram, when when it is shift, then slow clock will be when it is shift phase, whether it is stuck at or TDF, slow clock will be propagated. Both for stuck at and TDF, slow frequency clock will be propagated. If it is capture, if it is stuck at, slow frequency clock will be propagated. If it is TDF, then fast frequency clock will be propagated. And this clock gator only, it decides how many clock pulses have to be propagated during capture. Okay. So the complete structure of OCC, you can actually go through. Like this, just one block I have told. Complete structure of OCC, you can also go through that also. Okay.
Yeah, okay.
So there are actually two ways to detect transition delay faults, right? What are the two ways?
Transition delay fault, ma'am.
Yes.
Is it LOC and LOS, ma'am?
Yes, correct.
Yeah, ma'am. I had a doubt in that means I was I would asking you to explain that one at last.
Which one?
Yeah, LOC about LOC and LOS, ma'am.
Okay. So LOC is launch on capture. So here if you see LOC, how you will be having, this is scan enable. So here you are having this A pulse. This is the last shift pulse. And this B and C are the fast clock pulses. B and C. Okay. So these two are the fast clock pulses. BNC are fast frequency clock pulse, fast frequency clock, and A is slow frequency clock. Okay. So you want me to explain the difference between LOC and LON?
Yeah, ma'am. LOS and LOS,
Okay.
and how can we detect that?
Yeah. Okay. So this is LOC. Both the capture pulses will be, both the fast frequency clock pulses will be there in the capture phase. That is when scan enable is equal to 0. So you just consider an example like this. This is D, this is Q, this is SI, and this is D, and this is SI. Here you are having Q, and here you are having Q. This is Q here. Okay. So this is only net P. This is net P. So my aim is to detect slow to rise fault in net P. So my aim is to detect slow to rise fault in net P. So let me just copy this. I will consider 3 pulses. What will happen during A pulse, what will happen during B pulse, and what will happen during C pulse. So in this net P only, the tool, we are going to detect a slow to rise fault in this net P. This is only that net P. This is only that net P. So the tool will, we are going to detect a slow to rise fault in net P. So what the tool will do? The tool will try to bring a rise transition in net P, and it will try to see. So 0 to 1 transition it will see. It will try to bring at the end of C pulse. If this flop, if it is holding 1, then there is no slow to rise fault in net P. If it is holding 0, then you are having slow to rise fault in net P. So now what the tool will do is, so here it is trying to bring a slow to rise fault. So first what the tool will do, I'll consider this as A pulse. So during A pulse, the tool will try to write a 0 value in this net P. So if at this particular net, if 0 has to be there, then this flop should be holding a 0 value during A pulse. Only then at its output, 0 will be there. Now during B pulse, what will happen? B pulse is coming during the capture phase. B pulse is coming during the capture phase in LOC. Okay, B pulse is coming during capture phase. So what will happen? Whatever value is there in its D input, that will get captured into this flop. Now the tool again, it has to bring a slow to rise fault, right? So it will try to bring a rise transition. So here previously it has written 0. Here it will try to write a 1 value. So here if it has to have a 1 value, then at this flop should be containing a 1 value. Only then at its output you will be getting a 1 value here. Okay. So now what will happen is, if this flop has to hold a 1 value here, then before this B pulse, at its D input 1 value should be there, because only then when the rising edge of this clock comes, what will happen? B pulse comes, this value which is present in the D input will get captured into the flop. So here if at its D input, if it has to hold a 1 value, then the tool has to program this combo logic output in such a way during the A pulse itself. The tool has to program this combo logic output in such a way that the tool has to program the inputs of the combo logic in such a way that the output of the combo logic will be 1. So it can write, for example, I'm just writing it as 1 and 0. During A pulse itself, we should have written like that. You can even write 1 1 or 0 1 as well. Just for illustration, I've just considered 1 and 0. Okay, so this should have happened during A pulse. This is what will be there during B pulse. And during C pulse, if this net, if this net is not having slow to rise fault, this is not having slow to rise fault, then immediately it would have got transition to 1. So if this captures 1, then that means net A, this is a good value. Net P is not having a slow to rise fault. If it captures 0, then that is a faulty value. This net P is having slow to rise fault. That is, this net has not got transitioned to 0. So this is how using LOS, the tool will try to detect using LOC, the tool will try to detect the fault. Same way, now if you consider LOS. Now if you consider LOS, LOS is launch on shift. LOS is launch on shift. So this is the scan enable. Okay. So this is A pulse. And okay, launch on shift, what will happen? This is A pulse. Okay. And here one fast clock pulse will come during the shift phase itself. One fast clock pulse will come when scan enable is 1. And the other thing will come during the capture. Okay. So one fast clock pulse will come during shift phase itself when scan enable is equal to 1. Okay. The other fast clock pulse will come during this one, capture phase. This is B pulse and this is C pulse. So B and C, they are fast frequency clock pulse. Fast frequency clock. So same thing. Same thing only. We are going to detect slow to rise fault in net P. Okay. So I'll consider in the same way. 3 scenarios I will consider. Sorry, for A pulse, what will happen? For B pulse and for C pulse. This is A pulse, and then this is B pulse, and then this is C pulse. So what will happen now if it has to get a, okay, let me just consider this to be net P. This is only net P. So here only we are trying to bring a slow to rise transition. So slow to rise transition we are trying to detect here. So concept is the same. The tool will try to bring a 0 to 1 transition in net P, and at the end of C pulse, it will observe the value which is stored in this particular flop. If it is holding 1, then there is no slow to rise fault in net P. If it is holding 0, then there is a slow to rise fault in net P. Okay, during C pulse, after C pulse, it will observe. So now what has to happen? So previously, it will try to bring a slow to rise transition. So this has to be 0. First, it will try to bring a rise transition here. So here it has to detect a slow to rise transition. So slow to rise fault. So it will try to bring a rise transition in net P. So here it is 0. So if it is 0 here, then this flop has to hold a 0 value. This is during A pulse. Okay. Now, during B pulse, what will happen? It has to bring a 0 to 1 transition. So during B pulse, what will happen? This net, it will be given a 1 value. If this net has to be given a 1 value, it is bringing a rise transition in B, 0 to 1 transition. Sorry, it is bringing a 0 to 1 transition in net P. So here it will try to put a 1 value. If it has to put a 1 value here, then this flop must be holding a 1 value. So if this flop has to hold a 1 value, so B pulse at where it is coming? B pulse is coming when scan enable is equal to 1. That is during the shift phase, this B pulse is coming. So whatever value is there in the SI pin of this particular flop, that value only will be coming into this flop, will be going into this flop during the B pulse, because B pulse is coming during the shift phase. So here if it has to be 1, then at A pulse this has to be 1. Only then this output net will become 1. And during C pulse, as usual, like if this net is not having a slow to rise fault, then it would have changed to 1, and this is a good value. If it is having slow to rise fault, then it will be 0. That is a faulty value. Okay. So what are the observations which we have actually seen here? So the observations which we have seen is, first is LOC. It will have, LOS. LOS has more coverage. LOS has more coverage compared to LOC. So why? Because as tool has more controllability. As the tool has more controllability on LOS than LOC. Okay, LOS, it has more coverage compared to LOC, as tool has more controllability on LOS than LOC. So what it means is, the tool brings the transition value, through the shift path in LOS. Transition value through the shift path in LOS. Whereas in LOC, tool has to program the combo logic. To get an appropriate value at the output of the combo logic to create the transition. So here if you see in LOS, the tool is bringing the transition value through the shift path itself. It is not programming this combo logic. It is trying to bring the transition value through the shift path itself. But LOC, it has to program this combo logic. Okay. So if suppose the tool is not able to bring the appropriate value. Here in this case, it is a very small OR gate we have considered. Suppose if it is a big combo logic, and if the tool is not able to bring the appropriate value at the output of combo logic, then the faults that require this value will not get detected. Faults that require that value will not get detected. So suppose you consider that in this case you are having some big combo logic. If you are having a big combo logic, suppose at the output of the combo logic, if the tool is not able to bring this one value, then in that case we will not be able to detect this net T slow to rise fault. So that is why LOS has more coverage compared to LOC, because in LOC the tool has to program the combo logic. If it is not able to bring the appropriate value at the output of the combo logic, then those faults will not get detected. Like whichever fault require that particular value, those faults will not get detected. Okay. Second observation is LOC, it requires more patterns than LOS. As same thing as tool has to control the combo logic. Okay. LOC, it will require more patterns than LOS because the tool has to control the combo logic. Even though like LOS has more coverage and LOS requires less patterns, there is a major limitation in LOS. But there is a major limitation for LOS. So what is that limitation? Controlling scan enable is extremely difficult. So the scan enable. So this is the A pulse. This is B pulse. And this is C pulse. Okay. So this is A pulse, this is B, and this is C. So what will happen? Before C pulse comes, scan enable should be made 0. Has to be made 0. So this is very difficult. To get it. So that is why, therefore, industries mostly don't use LOS. Don't use LOS. So this is what is LOS and LOC.
Yeah,
So,
okay, ma'am. I have a doubt. Means, what about in this scenario? Between two flops, one AND gate is connected. One of the input of AND gate is connected to output of first flop, and other input is from primary inputs. And B net is we have to means B net is having slow to rise fault. How to explain their LOS and LOS, ma'am?
so here, right, whenever if any flop input, if it is connected to primary input, right, like this, through pad, it is coming, and if it is like this is the primary input. If it is like this, then like these paths. So if you are having something like this, say for example, you are having something like this. This is something else I will say. Okay. This is coming from OCC output. So here you are having some pad. Here you are having the pad, and this is actually connected to the primary input. So in these parts, right? In these parts, wherever I have marked with red, and also these parts, something like this is there. D and Q. SI. This is SI. And here you are having this one. This is the OCC output. So some combo logic is there. Again, it is coming from pad, and then it is connected to the primary input. So in these parts, wherever I have marked with red, right? In these nets, our tool will not bring a transition. Our tool will not bring a transition if it is connected to primary input. Why? Because inside the chip, we have high frequency TDF domains. High frequency TDF domain. So it will be around like 500 megahertz to 1 gigahertz. But pads, they do not support such high data rate. But pads don't support such high data rates. High speed data. So they can support only up to 150 megahertz. Around 150 megahertz. Around that range they can support. So what our tool will do is, our tool holds primary input to a constant value. Constant 0 or 1 during capture phase. So transition cannot be launched from PI. So this is one reason. This is actually one reason why we can expect only around 80% coverage in TDF. Why we can expect only 80% coverage in TDF. But in these cases, in these places, you will be able to bring the tool will be able to bring the transition. At these nets, tool will bring a transition. Tool will be able to bring a transition. As clock of these flops are coming from PLL through OCC. Are coming from PLL through OCC. Okay. So only in the path where directly it is connected to primary input, or through some combo logic if it is connected through a from primary input through some combo logic it is going, and it is going to the D input of the flop, means at these nets the tool will not be able to bring a transition. Okay, so this is one reason why our TDF coverage we can achieve only 80%, 80 to 85% coverage in TDF.
Yeah, okay, ma'am.
And yeah, my actual question was, so here if you see, what is LOS? LOS was, in LOS, it is like this, right? This is scan enable. So this is the last shifted pulse, A pulse. And this is one fast clock pulse, B pulse. And this is one fast clock pulse, C pulse. It was like this. This is A pulse, last shifted pulse. This is the last shift pulse. Last shift pulse. This is B pulse, B pulse, and this is C pulse. So this A is slow frequency clock, and B and C are fast frequency clock, fast frequency clock. So during that OCC, we had said, right, during shift, whether it is staccato or TDF, we will be propagating slow frequency clock. If it is transition, during capture only, if it is staccato, we will propagate slow frequency clock. If it is TDF, we'll be propagating fast frequency clock. How we are able to propagate? How we are able to propagate this fast frequency clock during shift phase? When scan enable is 1. So how are we able to propagate this?
Yeah, I am not getting, ma'am. You will explain.
Okay. So the answer is can enable will be pipelined and then used if we use LOS technique. Just a minute, I'll just take a diagram. So this is what is a pipeline scan enable structure. So this clock, whatever you are able to see here, that is the OCC output. This clock is the OCC output, and this SC pipeline enable, this is the control signal. So it will be controlled using TDR, and this will be equal to 1. It will be controlled using TDR. So when it is like AND gate, it will be controlled to 1. If it is OR, it will be controlled to 0. So here you will be having this 1. And this output, this scan enable, this is only called as the pipeline scan. Like we'll just name it as PE. PE, this is the pipeline scan enable. Pipeline scan enable. This pipeline scan enable only will be going to the flops. Okay. So now we'll see what happens. So here if you see, oh sorry. So here if you just see, this is like 1, right? So scan enable. So if you consider here at this pulse, scan enable is 1. So here scan enable is 1. So what will happen? This is 1. Output of this flop will be 1. This is also 1. Output of this OR gate, so this AND gate output will be 1. This scan enable is already 1. So this is the pipeline scan enable, that will also be 1. So at this point, pipeline scan enable is 1. So it will be carried till the next rising edge. Again at this rising edge, it will check. So scan enable is 1 here. So again, what will happen? So let me just copy it and paste it here. So again, what will happen? This will be 1. This is 1. So again, scan enable is 1 at that time. So here this will be 1, this will be 1, this will be 1. So this pipeline scan enable is also becoming 1, and it will be carried till the next rising edge. Now what will happen? At this pulse, it will see. Okay, it will see. So scan enable is 0. So what is happening? Scan enable is 0. So this will actually be equal to 1. This is 1. So scan enable is 0. So here it will be 0. The output here it is 0. Here it is 0. So what will happen? Pipeline scan enable will be equal to 0. So here if you see, pipeline scan enable, here after a small amount of delay, it is becoming 0. This small delay is because of the clock to queue delay of the flop and gate delay. This flop's clock to queue delay, and because of this gate delays, after a small amount of delay, it is becoming 0. This delay is because of clock to queue delay of flop and the gate delay. So after this will become 0. So it will be carried till the next rising edge. Again at this rising edge, what will happen? It will check. So scan enable is 0. So what will happen? I'm sorry. So this will become this is 1. Scan enable is 0. So here it will be 0. This will be 0. This will be 0. So here it is 0. So here also again it will be 0. It will be carried till the next rising edge. So this is how it happens. So original scan enable, if you see, it is like this fast clock pulse is coming when scan enable is equal to 0 phase only. But if you consider pipeline scan enable, then this fast clock pulse is coming during the shift phase. Okay, when scan enable is equal to 1. So this is how we are able to bring the fast clock pulse during the shift phase. Okay, when we enable LOS. So when LOS is enabled, this pipeline scan, through this pipeline scan enable structure only will be used. Okay. Okay. So yeah, I'm having these questions only to ask now.
Yeah, ma'am, I have a small doubt. Means EDT, ma'am, EDT, we are having the advantage of means reducing test data, right?
Yes. Test
Yeah,
data
some
volume.
test data volume. But someone interviewer asked me that if number of patterns increases, test data will be increases or decreased.
Okay.
Yeah,
So
some
let me just explain that. So test data volume, right? Test data volume.
yeah.
So formula is number of patterns into number of shift cycles per pattern, number of shift cycles per pattern into number of channels. Number of channels. So if number of patterns increases, if it increases, then what will happen? Test data volume will increase. But number of shift cycles per pattern, if you consider shift cycles per pattern, okay, that will be more without compression than with the compression. So if you consider without compression and with compression, without compression and with compression. So number of patterns without compression, number of patterns will be like 1500, just assume. Number of patterns with compression, it will slightly increase. So we'll consider around 2000. So like around 500 patterns have got increased. But number of shift cycles per pattern, it will be around 500 without compression, means number of shift cycles per pattern with the compression, it will be around only 50. So compared to this difference, compared to number of patterns difference, number of shift cycles per pattern is more. Number of shift cycles per pattern difference is more. Here the difference is only 500. But here if you see 550 it is there. So around 1500 plus this is like 500 minus 50, how much it is coming? 500 minus 50.
450, ma'am.
Yeah, 450. The difference is 450. So compared to number of patterns difference, number of shift cycles per pattern difference is more. So if you are now the number of channels, it is going to be the same only, because we are going in this formula, we have to substitute the top level channels. We'll just consider that to be 2. Now if you just substitute in this equation test data volume, so it will be like number of patterns into number of shift cycles per pattern into number of channels. So this you will be getting around like this, these many bytes. Okay, so which is nothing but 1.5 MB. This is for test data volume. This is the test data volume without compression. Now with the compression, if you consider, this will be 2000 into 50 into 2. So this will give you only around 0.2 MB. So when you consider with the compression and without compression, test data volume will be less for without compression.
Yeah, ma'am. Number of shift cycle, if it is reduced, test time will be reduced, no, ma'am. How if number of patterns is related test data volume?
No. This is the formula for test data volume. This is the formula for test data volume. Number of patterns into number of shift cycles per pattern into number of channels. So you have to substitute in it and you have to take with compression and without compression. So with compression and without compression, if you compare, with compression, test data volume will be less compared to without compression.
Yeah, okay, ma'am. Yeah, ma'am. Before interview, at the interviewer, I explained this only, ma'am. But he asked like that, if number of shift cycles will be test time will be reduced. How number if number of patterns is more test data, how it will be reduced? He asked for me.
Yeah, you have to substitute here and you have to tell like this. You have to take an example and you have to substitute and you have to tell him like how it is reduced.
Yeah, okay, ma'am. Yeah, ma'am. Is there any placements arriving for institutes, ma'am? I didn't got any placement drives. I didn't got any
Just a
interview
second, sir.
from institute people. I didn't got any drives.
You can check with Manohar, sir.
Yeah, okay, ma'am. Okay, thank you.
Okay. Or you can message in your personalized group.
Yeah, okay. Okay.
Okay. You're from October batch?
No, ma'am. I'm from July batch, ma'am.
Okay. So DFT advanced October, right?
Yeah. DFT advanced October.
Okay. Yeah, you can message in your personalized group.
Yeah, okay, ma'am.
Okay.
Yeah, okay. Thank you.
Okay. Thank you.
Thank you.